Hey everybody, this is Larry. This is day 30 of the May Leetcode challenge. Hit the like button, hit the subscribe button. Let me know what you think. Oh, and I clicked on the June challenge. Whoops. Uh, yeah, let me know how you solved today's problem and let me know what you think. Cool. K, K closest points to origin. We have a list of points on the plane. Find the K closest points to the origin 0, 0. Here, the distance between 2 points on the plane are early in distance. You may return the answer in any order. The answer is guaranteed to be unique. Okay. So I think there are a couple of ways you can do about this. The most naive way would be, well, just do some kind of brute force thing. And we can also sort by the distance as well. And when we sort the distance, we take the first K, that would be good enough. And the complexity of that would be dominated by the sort, which is n log n. In this case, it would be 10,000 10,000 times log 10,000, right? Which is going to be fast enough, and you can write this in like 5 lines of code or something, or not even probably, just probably something like, probably something like this, right? Where you sort points by key is equal to lambda of, let's just say p for points, p of, oops, p sub 0 times to power 2 plus p sub 1 power 2, right? Something like that, right? And we're waiting for testing. While we do that, we put in the second one. Why not? Still pending though. Let's run the second case real quick. All right. And that's going to get you accepted, right? So we finish solving it in about 1 line of code, and it's a really messy Python statement, I admit, but is the n log n plus k, I guess, but where k is less than n, so it's going to be dominated by n log n. But the question is, can you do better, right? The n log n is good, but we can actually get it down to n log k by using a heap. Let's get to that. Let's try that for a second. So in Python, a heap is a little bit weird in that it's queued. Because it is a min queue instead of a max queue, which is a lot of different languages library uses a max queue, but Python's most common heap library uses a min heap, so I would do that. And then the question from that is, do we use a max heap or a min heap? Well, we want to contain the smallest k elements, right? So in that, we want to be able to push things into the queue if they're smaller than elements inside the set. And for that, we have to get the largest element in the heap, so that if your current element is smaller than the largest element, then you put it into the heap, and then you remove that element or something like that. So in that case, even though it might sound a little bit weird, and it took me a little bit of time to kind of make sure that I was right on stuff like this when I was learning heaps, is that in this case, we want to get the max heap. So let's do that. So first of all, let's just do point by point for actually x, y in points, and we push the, is it heap push? Quite sure about the syntax anymore. But basically, we push into the heap the what we call a priority, and in this case, we want the priority to be the distance, right? So x power of 2 plus y power of 2. And in theory, that should be good enough. But again, the reminder is that because we want a max heap, but this is a min heap, we're going to do a little bit of a hack to make this into converting a max heap to a min heap, at least for integers, because we can just convert it to the negative format, right? And we actually don't care about this value anyway, and ultimately. So in this case, if we do this, it's going to be essentially a heap sort. So what we actually want to do is only if length of heap is greater than k, or I guess greater than equal to k, it should be only equal to, but if it's greater than k and the first element of the heap is bigger than, okay, let's put the score is equal to here. Score priority. So heap of 0 looks at the first element of the heap, which is in this case the maximal element. So if and we have to convert it back to the actual original priority by making it negative. So it's a little bit hacky for that reason, but you could also have overloaded the comparator, for example. But let's say this is the score. Oh, actually, to keep it simple, we'll keep the score there. But let's say the top of the heap, if that is bigger than the score, I just want to see guaranteed to be unique. Okay. So there's no tiebreakers. I think that was what I was looking for. If the top of the heap is bigger than score, then we want a heap pop. And then after we heap pop, this will be we put the heap back in, and then at the very end, let's return the score. Return the list of points. Let's just do results. Actually, we don't even. Okay, you still have to convert it back to a list of lists, so that's okay. So let's just return heap. So normally in other languages or other APIs, you may need to keep on popping to get the ordered result. But in this case, the reason why we're doing what I'm going to be doing now is that you may return the answer in any order. And because the answer could be in any order, and the heap in Python is just an array, we can actually just convert it straight back. Let's run it again now. Oops. Oh yeah, that's right. Sorry. This should be the 0, 0 because this is the first element that contains the score, and this is just for the top. Syntax is a little weird. I think I could rewrite that to contain to abstract this to a variable so that it's clear for readability. But yeah, let's submit it again. Ooh, wrong answer. Oh, oh, that's a little. Well, that's why we test things, and I guess I didn't test enough. But maybe I have the signs wrong. So if the top of the heap figure out a score, we pop the heap. That seems right. Let's print it out just for debugging. Oh, I see. Okay, so the reason why this is wrong is because we didn't handle the tiebreaking case well, and that's why you have to be a little bit careful. So if this is equal to, we also want to pop, but that doesn't make sense, does it? Oh, I see. I was just being a little bit careless. So this is okay, but we also want to make sure that we only want to push in the heap if the top element is, if the score is better than the top element, right? I think this is also a little bit wrong. If it's equal to, we can also push. because there'll be no tiebreakers. I think to be honest, I feel like right now I'm handling the edge cases pretty poorly as a result. I think what I'm doing now is not thinking in terms of invariance, and the invariant is why I'm getting this a little bit confused. So let's see. If heap is 0, then okay, and then if the top of the or if the top of the heap is greater than score, then we want to push in the heap. Okay, actually, let's make this such that I think this should be okay. Because this is saying if the size of the heap is less than k, or if the size is exactly. No, I think this isn't even necessary, actually. Okay, let's submit this again. Okay, cool. Yeah, so I think it's worth. Yeah, sometimes even if you've done it a lot of times, you have to make sure that you test. And I made the critical mistake to not test. So definitely I recommend testing, even if you're confident about it. So what I was doing, what basically this algorithm is saying is, okay, that's top. If it's greater than or equal to k, and the top of the heap is, if the top of the heap is bigger than what you're putting in, then let's pop the top of the heap, right? And then later, if the size of the heap is less than k, then we always push no matter what. And I think that allows us to have a better edge case conditioning, just to make sure that it handles more edge cases. So what's the complexity here, right? Well, the invariant in this thing is noticing that the heap is always going to be less than or equal to k. And each of this heap operation is going to be log k at most. And because we do this n times, this is going to be n log k. And in terms of space, this is also O of n, same as the sorting, because depending on how you want to count the sorting, if you do it in place, I guess technically it's O of 1, but yeah, depends how you want to count the sorting. But this is pretty straightforward. Heap comes up all the time in interviews and definitely all the times in competitive programming. So definitely get used to it, get practice with it. So I like this question for that reason. I think one more thing that I didn't point out is that technically the distance is the square root of this, but because the function for square root is monotonically increasing, then that way you could say multiply by itself to get rid of the square root so that we don't have to deal with floats, and then we could keep these in integers, and also it's a little bit faster because we're not using square root, which is an expensive operation. Cool. I think that's all I have for this problem. It's heap. I love heaps. Definitely practice heaps, and yeah, that's all I have for this problem. I'll see y'all tomorrow for the last problem of the day. Have a good night, and I'll see you later. Bye bye.